Everyone, welcome to our very next video for STEMEY AP Physics 1. Today we'll be talking about simple harmonic motion. So first up, what is simple harmonic motion? So simple harmonic motion is a very special type of periodic motion where the restorative force is directly proportional to the object's displacement and acts towards equilibrium. So that is a little bit confusing, but the main point is something like a pendulum or a spring in which there is a consistent backwards and forwards movement as the object is coming towards equilibrium. And that is due to the restoring force, which is a force that acts opposite to displacement in order to bring a system back to equilibrium. So here's just going to be a short video that'll be really helpful to understand a pendulum, which is a type of simple harmonic motion. So as you can see in this video, the pendulum just moves back and forth and back and forth. And that is exactly what simple harmonic motion is, because this ball is always trying to come back to equilibrium, which is this middle point right there. So some really key things to keep in mind when we talk about simple harmonic motion is that it really can't happen in real life. That's because there's often some sort of friction or air resistance that makes it impossible to maintain perfect simple harmonic motion. In a spring, that's friction, one between the actual spring, and then also with air, of course, and then likely to be on a table, which causes friction. With a pendulum, we have air resistance and friction of the string on the place that it's attached. Additionally, with pendulums, it can't actually happen if the angle is greater than around 15 degrees. Some people say 10 degrees, which allows it to be even closer to simple harmonic motion. But the concept is the smaller the angle, the closer it'll be to simple harmonic motion. And now oscillations. So oscillations is actually how we often measure simple harmonic motion because it provides that really great periodic image of what's going on. In a wave, the three really important topics when we cover simple harmonic motion is amplitude, which is here, which is the distance from equilibrium to the maximum. We have period, which is the time for one cycle, which is measured in seconds, and frequency, which is the number of oscillations per unit time. If we keep that time as seconds, we use the unit hertz. And now graph. So this is where the oscillations graph really becomes helpful, because in simple harmonic motion, because it's such a periodic movement, the shapes of the graphs are really consistent and you can see certain patterns in them. Here will be just a quick video while I explain what they are. So displacement is usually a cosine graph, with A being the amplitude, which is the maximum distance from the equilibrium. And it's a cosine graph because a lot of times you'll start at your maximum position away from equilibrium, which allows it to move back and forth. Velocity is a sine curve, which varies depending on the displacement, the force, other issues as well. And it is a sine graph because when you pull it to the maximum position, you have zero velocity. Therefore, your starting position is at zero and thus a sine curve. For acceleration, we have a negative cosine curve because the acceleration will pull you back to equilibrium, which causes a negative acceleration towards the equilibrium position. And therefore, you can see that all of these are related and really helpful when we talk about simple harmonic motion. And now types of simple harmonic motion. So of course, we have springs, which is one of the most traditional ones. And that's just a spring being pulled or stretched from an equilibrium position back and forth. And that causes a force, as you see here, that's pulling the object right back to its equilibrium position right here, which we call the spring force. The period, and this formula is super helpful, is really consistent in spring simple harmonic motion. We have mass of the object that's connected to the spring, and K, which is Hooke's constant. And Hooke's constant is a constant that varies, ironically, per spring. Each spring, depending on its stretch, depending on the metal, depending on the size, has a varying Hooke's constant. And therefore, you can't really know what it is unless you measure it through an experiment or if it's given to us in the problem. But it's not something that you can just search up. And for the force of the spring, you have, again, Hooke's constant times x, which is the displacement that you get at a certain position, and it's negative because it's always pulling the object right back to equilibrium. And vertical springs. So again, conceptually, this will be pretty similar to the horizontal springs. The one small nuance is that it is impacted by gravity. And we can see here the equilibrium, but gravity will pull it down a little bit, which causes it to bounce back and forth. So the net force now, instead of just being the spring force like it was in the horizontal one, we also have to account for gravity, which will be in the opposite direction. And therefore we get that the net force is actually the negative of the spring constant times the displacement minus mg. But all the other properties, including period, are just like the horizontal spring. And the last type of simple harmonic motion that we're going to cover right now is going to be pendulums. And this is a little bit more complex because of the angle and with gravity. But again, we do have the formula for the period, which is actually very similar to the spring one, which helps with memorization, which is that it's 2 pi times the square root of L, which is the length of the string attached for the pendulum, divided by gravity or acceleration due to gravity, better of, which on Earth is approximately 9.8. But of course, if we go to a different planet, it will change. And just to reiterate that the properties of simple harmonic motion really only apply to under 15 degrees, but of course, smaller angle, better simple harmonic motion, which is very important to keep in mind when we actually create these sort of situations. And now our last topic in all of this is going to be energy. So just a little bit of review right now. Of course, we have our gravitational potential energy right here, which is mg times the height, which is usually h, but here we put delta x. And we have kinetic energy, which is the energy due to motion. So we have 1/2 mv squared. A newer one will be the elastic spring energy, which is 1/2 kx squared. Again, k is Hooke's constant, which varies depending on the spring. And there is no formula, just to keep in mind, for the pendulum ones, because that is just going to be gravitational potential energy at a certain angle depending on the angle of the pendulum. But what's nice is that the elastic potential energy is very similar to the kinetic energy formula, just changing up the variables of it, which is helpful when we try to memorize these formulas. And now we're just going to go into, again, the conservation of energy, which is pretty common in all of physics topics, but especially important in simple harmonic motion. And that is that the energy, of course, in the system will remain constant in AP Physics 1 world, where we don't lose energy to friction or any other air resistance. So that allows us to say that the potential energy is max when the system has max displacement, and velocity is max when the displacement is minimum. So if we want to think of it like a pendulum, when we're at the highest position, because all the energy is in gravitational potential energy, we have almost 0 for velocity, 0 meters per second at its very peak. But then as we come down and gravitational potential energy is converted into kinetic energy, at the bottom we have the very maximum speed. And then again, back to the top with 0 velocity and highest height, and then we come back down. For spring, pretty similar. When we're compressed all the way here, all of the energy is in the form of the spring potential energy, so the velocity is basically 0. Then we come to the middle, and here the kinetic energy will be at its max because we have almost no spring energy because there's no extension of the spring, and then again back and forth and back and forth. So just to reiterate conservation of energy, the total energy will be equal to the kinetic energy plus the potential energy. In a pendulum, that's gravitational potential. And in a spring, that will be the spring potential energy, unless it's a vertical spring, which also you have to account for the gravitational potential energy. And we know that the total energy is equal to the maximum kinetic energy, which allows us to solve for the speed at either the bottom of the pendulum or at equilibrium of the spring. And it's also equal to the max for the potential energy. So for here, we can find the height in a pendulum, and we can find the maximum displacement for a horizontal spring. So now we're going to be doing some practice problems. So yeah, get ready for those. So first up, Imagine you could travel to the moon, where the acceleration due to gravity is 1.6 meters per second squared. What would be the period of the pendulum? I'll give you 5 seconds to pause that and give it a shot, and then we'll come back. So for this problem, it is basically just using the formula from one of the previous slides, and that is that the period of a pendulum is equal to 2 pi times the square root of the length divided by g. So we have 2 pi, a constant, divided by the square times the square root of 1, because we have that the length is 1 meter, divided by 1.6, because we are no longer on Earth, so it is not 9.8, but rather 1.6, which we get 4.97 seconds. And now our next problem, which is directly from an AP Physics 1 practice problem. Block P of mass m is on a horizontal frictionless surface and is attached to a spring with a spring constant or Hooke's constant of k. The block is oscillating with period Tp and amplitude of AP about the spring's equilibrium position, which is just saying that the middle position. A second block Q of mass 2m is then dropped from rest and lands on block P at the instant it passes through equilibrium position, as shown on this image. Block Q immediately sticks to the top of block P, and the two block system oscillate with a period TPQ and an amplitude of APQ. So here are the two problems. Give it a shot. We will come back in around 5 seconds. So for the first one, we have exactly the equation for the period when we're dealing with a spring. So that is 2 pi times the square root of m, which is the mass divided by k. And of course, we're just dealing with variables here. So we can solve for one, the period of when it's just block P, and then the period when it's both blocks. And then when we divide it in the way that it's asked here, we get the square root of 3. And for this next problem, it is a slight bit more complicated because we have to use a lot of concepts regarding energy. So first, actually, we're going to be talking about momentum when we deal with this problem, because we're seeing that there's going to be a conservation of momentum. And when we solve for this, we can see the velocity once the block is dropped onto block P. So of course, before block Q is dropped on, we just have the mass, which is m, times a velocity we're just going to keep as v for now. But then afterwards, we have 3m, because it is a block of 2m plus another m from P, times a velocity that we're just going to be labeling as VPQ. And as we simplify, we can get that 1/3 of Vp is equal to VPQ. And now we're going to go into more of the energy material. So first up, we have kinetic energy. And this is just a matter of using the numbers that we got in the conservation of momentum and plug it into the kinetic energy formula. And we can see here that as things simplify out, that 1/3 of the kinetic energy of P is equal to the kinetic energy of both blocks. So it becomes clear that the kinetic energy of P is going to be greater than the kinetic energy of both blocks put together. And using our knowledge from conservation of energy, we know that this directly applies to the potential energy, in this case, potential spring. So we know that the potential spring energy of P is going to be greater than with both blocks. Then we can just use our formula of potential spring energy, which I have put A here because we're going to be dealing with amplitude, but of course it's just equal to displacement that I labeled as x in previous slides, because amplitude is the maximum x position. So we can put that formula in, and we clearly see, because the k will be the same, the spring's the same, 1/2 is a constant, that the amplitude of P is greater than the amplitude of both blocks in this system. And now our next problem. So again, just pause the video for 5 seconds and give that a shot. So the really important concept when we deal with this problem is understanding how to get the initial height. And that's what I've drawn this triangle here for, to see that we can basically just be using trig. So the height here, which will be that height here, which is the height from the 0 position of this pendulum, is the total length of the string which will be this string, which is exactly just that because it'll swing back down and have that as the 0 position, minus this length right here. And that we can get using the trig that we're provided here with the 14 degrees. Because of similar triangles, we can see these two will be parallel and that line will come through. So we know that this angle as well is equal to 14 degrees. And then using trig, we can figure out that that will be the hypotenuse of 0.5. So therefore we can find that this length will be the length of the total string times the cosine of this angle, which will also be 14. And therefore we can use our ideas here and combine that with the energy, so gravitational potential energy, so we find how much total energy the pendulum has at the beginning. This mgh, m will be mass, g we're just going to be using 10 to keep things simple instead of 9.8, and the formula from right here, so the length of the string, which is 0.5, minus 0.5 cosine of 14 theta, just exactly what we talked about before. And we got that the total mechanical energy in the beginning is 0.74261 joules. But the final, which is what we're going to be dealing with when the angle is at 7 degrees, is going to be using the conservation of energy. So at that position, which will be around there, right, just halfway through, we know that there's going to be both gravitational potential energy and kinetic energy. So we have to account for both. Fortunately, we have all the values for this situation. Again, mg, just like before, times the same formula but with a different angle because we're at a different position with a different height. But now we also have to plus the 1/2 5 times v squared, which is how we're going to be able to solve for the speed of the pendulum. And of course, we know conservation of energy, this value, 0.7 around, is going to be the same at the position at 7 degrees. Then we can solve for v and get that it's approximately 0.4717 meters per second. And this problem is a little bit more complicated, but it's really, really important to understand this formula right here, because that's basically how we're going to solve most of our problems when it comes to energy, when it comes to pendulums. And now our very last problem is going to be with some graphs. So for the spring block oscillator shown right here, sketch these 6 graphs: the displacement, the velocity, potential energy, kinetic energy, force, and acceleration. Just to give a little pointer, if you draw it in this order, it will be more helpful. So just pause the video, I'll give you 5 seconds to try that out, and then we'll get back. So here they all are, and we're going to be using the markings here with C, A, B. If we start at A, of course, displacement will be 0 because that will be the 0 point here. And then we go to a positive x when we get to B, back to A, which is 0, then to negative x, and back and forth. With velocity, what's helpful is to look actually at the displacement graph. You can know intuitively that when you're at the maximum of B, you're going to have 0 as a velocity because you're not going to be moving and it'll just hit your maximum point. And then you'll get 0 again at point C, but you'll have your maximum at A. What you can also do is look at the slope of your displacement graph and see that at this initial point, the slope is at its maximum and is positive. Maximum and positive. And then when we get to B and when we're at C, the slope of the line will be just straight right there, which is derivative if you know calculus. And then we get to the 0 here and the 0 here and onwards. Now for the potential energy, which is going to be just spring potential energy here. And we're not going to be accounting for gravitational potential energy. So we know that at the beginning, the spring is not being extended, and therefore the spring potential energy is going to be 0. But we extend at B and we extend at C. So therefore we had our max at B and C. What's important to keep in mind here is that energy is a vector, but not in the sense of direction. Therefore, when we're dealing with energy in this sense, it's always going to be positive because we're not losing energy, which is what signifies a negative sign. And same thing for kinetic. But what's cool here is if we use the knowledge we know from the potential energy, we can again just use it right there at the same place because they'll be the opposites because of conservation of energy. What you can also think about is knowing from the definition of kinetic energy, which is 1/2 mv squared. So when V is max, kinetic energy will be max, And when velocity is at 0, your kinetic energy will also be 0. And when it's negative velocity but maximum, we're going to have the same value as the initial because of the square, which allows it to be positive. And now we have force, which is of course really connected to the spring and how it's being extended. So we have 0 and then we get extended. But what's really important to keep in mind here is that force with spring is negative kx. And therefore, even though we have a positive displacement, we'll have a negative force because the force is pulling the box back to equilibrium, and therefore it's negative. But then it just follows the same pattern as we've been talking before with 0 because no extension, negative, 0, positive. And now acceleration. So there are a couple ways to do this. One is, of course, just following the force graph because F equals ma, and because the block and the mass is constant, m is just a constant, so F will be directly proportional to a, and therefore it's the exact same graph. You can also do it the way that we found the connection between x and v. You can do the same connection between a and v. The slope of the velocity graph, you can follow that through. So at a, you have a tangent, again going back to calculus, or a slope of 0, 0 right there, maximum but negative, maximum and negative, and then again 0, maximum positive, which is c, and then 0 again back at a. But yeah, you can see how all of these are completely connected with each other, and they all produce some sort of trigonometric graph. That is all from us today. We have more resources here, which will be linked in the comments below. Make sure to check those out, and also like and comment on this video, subscribe to our channel, and make sure to check out all of the other wonderful videos from STEMEY. Thank you so much for joining me here today.